Okay, so let's go over homework 2. Well, not all of it. Um, say number 41, the first problem, most people did just fine. So maybe I don't need to talk much about that. Um, yeah, let's talk about 42. 42 was the one where it says basically, suppose that this sequence is graphical, or yeah, sorry, let me start over. This sequence is graphical if and only if this sequence is graphical. That's what you're asked to prove in number 42, just to jog your memory of which one that was. And I saw a number of things that people did for this. So this is an if and only if question. So of course you have to suppose that this is graphical and then use that to prove that the other one's graphical, and then you have to do it the other way around, where you assume this one's graphical and you prove that that one's graphical. I saw people did a number of things that don't prove that a sequence is graphical. Like when you're assuming that this one is graphical and you want to prove that this one is graphical, I saw people just add up all of the degrees and verify that it was an even number and then say, therefore, it's graphical. Not really. The fact that the numbers add up to an even number does not make the sequence graphical. I also saw people verifying that these numbers are all non-negative, which they are, but just because these numbers are non-negative doesn't make the sequence graphical. Basically, as far as we have at our disposal, there's two ways to show that a sequence is graphical. One of them is to just describe or to draw a graph that has that degree sequence. That's the most direct way. Another way is to use one of these theorems like the Havel-Hakimi theorem that we proved in chapter 1, the one that tells you a sequence is graphical if and only if this other sequence is graphical, where you remove the first number and you subtract 1 from certain ones of these. So, yeah, those are that's basically the two ways to show that a sequence is graphical. In this one, basically, the answer is to just consider the graph complement. If you're supposing that this sequence is graphical, that means that there's a graph that has that degree sequence. And then what if you took the complement of that graph and looked at the degree sequence of the complement? Well, if there's a vertex of degree d1 in the original graph, what is its degree going to be in the complement? Well, in the complement, this vertex is going to be adjacent to everything that it wasn't adjacent to before. There's n vertices total, and it was adjacent to d1 of them. Also, one of the vertices is itself, and it can't be adjacent to itself. It's not adjacent to itself in the original graph. It's also not adjacent to itself in the complement. So we're really talking about the other n minus 1 vertices. We have a vertex here, and there's n minus 1 other ones. And out of those, it's adjacent to D1. And then in the complement, it's just going to be adjacent to whichever ones of these it wasn't adjacent to before. In other words, its new degree is going to be this. And similarly, the vertex that has degree D2, its new degree in the complement is going to be this. And so this is the degree sequence of the complement. To get the degree sequence of the complement, you really just do n minus each of one of these degrees minus 1. And that shows that this is a graphical sequence because we just described a graph that has that degree sequence. So that's the first direction, that if this is graphical, then this is also graphical. To get the other direction, it's the same trick, actually. if G has this degree sequence and you do the complement, then you get this degree sequence. And I guess, yeah, maybe just to really justify this clearly, say we have this degree in the original graph, and then in the complement, what would the new degree be? To get the new degree, you do n minus 1 minus the original degree. And then the n's cancel, the 1's cancel, and you just get a plus d1. In other words, if you start with this degree, then you do the complement and you get this degree. And similarly for all of these. So it goes back and forth. Right, so that's number 42. Let's talk about number 52. So 52, after doing it, I realized it was probably on the hard side, I'd say. But here's a solution. So just to jog your memory, this is the one that where you assume that G has order n, which is at least 4, and that the degree of every vertex is at least 2n plus 1 divided by 3. And what we want to show is that every edge is contained in a complete subgraph of order 4. So basically, if you give me an edge, I have to show that that edge is contained in a complete subgraph of order 4. In other words, I have to find 2 other vertices to make a total of 4. I have to start with the edge that you gave me, and I have to find 2 other vertices such that all of these edges, you have every possible edge among these 4 vertices, all the edges. So, how are we going to do that? Let me give sort of an overview of this. So I already drew this picture. Let me kind of draw it again. Say here's E. What I have to do is I have to find 2 vertices. First of all, to find maybe the first other vertex, I have to make sure that it's adjacent to this and this. And then I have to find another vertex that's adjacent to this and this. So that's going to be the first thing that I focus on, is just finding 2 vertices that are both adjacent to both of these. I have to find a vertex like this that's adjacent to this one, and a vertex like this that's adjacent to this one and this one. Of course, then I have to worry about this edge, because I need to make sure that that edge is also there, but I'll worry about that last. So I'm going to use the phrase common neighbor here. So if E is the edge x, y, like x is the name of this vertex and y is the name of this vertex, then this is a common neighbor of x and y, right? Because it's a neighbor of x and it's a neighbor of y. Also, this is a common neighbor of x and y. So, yeah, let me just start reading through this before I get too far ahead of myself. Like I said, we are considering an arbitrary edge in the graph, and we have to show that that edge, E, belongs to a complete subgraph of order 4. And I'm going to let E be the edge x, y. So I'm just giving names to the endpoints of the edge, and it's the same names I gave up here. So x and y are the endpoints of E. Okay. There are n minus 2 vertices other than x and y, of course, because there's a total of n vertices. Out of those vertices, at least this many are neighbors of x, and at least the same number are neighbors of y. Why am I saying that? Well, in the original graph, the degree of every vertex was at least 2n plus 1 over 3. And so x has at least that many neighbors, but one of the neighbors is y. so I went ahead and I subtracted 1 because I want to count all the neighbors of x other than y. So if I subtract 1 and I get a common denominator, this turns into 2n minus 2 over 3. Similarly, y has at least that many neighbors, but one of them is x, and so if I subtract 1 from this, that's how many neighbors y has other than x. Or y has at least that many neighbors other than x, I should say. Now, take a look at this picture. The set A here is supposed to represent the neighbors of x other than y, and the set B is representing the neighbors of y other than x. And just to remind you where we are, I'm trying to find 2 common neighbors of x and y. The common neighbors would be in the intersection of A and B. And so I'm interested in this intersection. So here's an observation. Out of all the vertices other than x and y, we know that there's n minus 2 of those. So n minus 2 is greater than or equal to the cardinality of the union of A and B. Because if this set is contained in that set, it's contained in the set of all vertices other than x and y. So this can't be more than n minus 2, because n minus 2 would be all the vertices other than x and y. Meanwhile, we know this information about unions of sets, that the cardinality of the union is, I can do the cardinality of one plus the cardinality of the other minus the cardinality of the intersection. A is at least this, because that's what we said, that at least this many are neighbors of x, and that's A. So A is at least this number, B is also at least this number, and when I add those together, I just get 4n minus 4 over 3, right, because I just did this plus itself. So A plus B is greater than or equal to that. And the intersection, I don't know, I'll just write the intersection. And what do I have here? I have an inequality. I have n minus 2 is greater than or equal to this number. And if I solve this for the cardinality of the intersection, I'm going to get n minus 2 over 3. Right, because I guess this is, there's a little bit of getting a common denominator here, because this one is 3n minus 6 over 3, and if I subtracted that over, I would get n plus 2 over 3. So yeah, just solve this for A intersect B, and you'll get that it's greater than or equal to n plus 2 over 3. That's good. Remember, my goal was to find 2 vertices in the intersection. Like, maybe here and here. And here I showed that the intersection is at least this. Remember that n is at least 4, so if n was 4, this would be 6 over 3, so that would be 2. So that's good. That's telling me that there's at least 2 vertices in the intersection. Now let's worry about the last part, because this just puts us in this picture, that I know that I have 2 vertices here and here, and that this one's adjacent to both x and y, and this one's also adjacent to both x and y. The last thing I need to know is that these 2 are adjacent, or that somehow there's 2 vertices that look like this and they're adjacent to each other. So I'm here in the proof. At least n plus 2 over 3 are neighbors of both x and y. That's what we just said. That's the cardinality of the intersection. At least that many are neighbors of both x and y. So I'm going to let S be the set of vertices that are adjacent to both x and y. In other words, S is this intersection here. Let V be any vertex in S. What I want to show, say this is V, I just want to show that V has a neighbor in S. If V has a neighbor in S, then I can use V and its neighbor in S as my two vertices because they're adjacent to each other and they're both adjacent to x and y. So if I can just find a neighbor of V in S, then I'm done. If V didn't have a neighbor in S, then how large could the degree of V possibly be? Well, V, the only neighbors of V would have to be outside of S if we're saying that V doesn't have any neighbors inside S. So the degree of V would be at most, I'll just count how many vertices are there outside of S. There's n vertices total. I'll subtract the number in S, or S has at least this number, and I have this inequality, so the inequality goes the right direction. So this is the total number of vertices, and I'm subtracting a bound on the number of them that would be in S, and I get this, but that's too small. The degree of V can't be that small. The degree of every single vertex is at least 2n plus 1 over 3, and this is a smaller number than that. So that would be a contradiction. In other words, V does have a neighbor in S. It's not possible for V to have no neighbors in S. So V must have a neighbor in S. And then, as I described, I'm basically done, but I just wrote another couple of lines on the next page explaining how we're done. Let W be the neighbor of V in S. So maybe this one can be W. And then the four vertices are X, Y, V, and W. They form a complete subgraph on four vertices, and it contains the original edge that we started with, which is the edge X, Y. So this vertex, this vertex, this vertex, and this vertex make a complete subgraph on four vertices. Yeah, so let's talk about 13 just a little bit. On this one, I would say if somebody had a problem, it was mostly having to do with the definition of connected to. So there's a definition of this on page 42. And yeah, if you're doing a math problem and you feel like you don't know the definition, you should really look it up or ask me. But so some people thought that U being connected to V in a graph just meant that there was an edge directly from U to V. It doesn't really mean that. It means that there's a path from U to V. So this definition is on page 42. U is connected to V if and only if G has a UV path. And by the way, G has a UV path if and only if G has a UV walk. This is a theorem that we proved in chapter 1. So I'm going to use this last statement as a definition for U being connected to, because it's all equivalent. U being connected to V if and only if there's a UV path, if and only if there's a UV walk. So I can use this as my definition. And yeah, other than that, this is mostly an exercise in just kind of translating what things mean. It's not that hard to prove these things once you realize what you're trying to prove. to show that something is an equivalence relation, and by the way, this is another spot where maybe there was some confusion on the definition of equivalence relation, but to show that something is an equivalence relation, you have to show that it's reflexive, meaning that just in words, everything has the relationship to itself. Since the relationship we're talking about is U is related to V if there's a UV walk. That means if I'm saying that U is related to itself, that means what I'm saying is that there's a UU walk. And of course that's true. It's very easy to describe a walk that starts at U and ends at U. I would just use this notation to describe such a walk. We use parentheses to describe a sequence, and the sequence is just going to have one vertex. It starts and ends at U. So that is a UU walk, and that's all we need to prove to show that this is a reflexive relation. There's two other properties that we have to show that make it an equivalence relation. We have to show that it's symmetric, which means in this context that if G has a UV walk, then G has a VU walk. That's pretty easy because if there's a UV walk, then you can just basically write that walk backwards and it turns into a VU walk. And I described that down here. Finally, we have to show that it's transitive, and that amounts to showing that if there's a UV walk and a VW walk, then there's a UW walk. So the transitive property is like there's three things. The first thing's related to the second thing, and the second thing's related to the third thing, and you have to show that that means the first thing's related to the third thing. That's the transitive property. And roughly speaking, that's true because if you can walk from U to V and walk from V to W, then you can put those two walks together and walk from U to W. And I described that more formally down here. But as you can see, it really just amounts to taking this walk and taking this walk and then putting them together. So I took this walk and put it here. This is the walk from U to V, and then this one picks up where that one left off. This one goes from V to W, and so I just put those together, and that takes me from U to W. Okay, what else? Yeah, so maybe the last one I'll really talk about is 16. This was another one that people had problems with. Maybe it was a little bit on the hard side. So this is the one where we're supposing that we have a disconnected graph with three components, and we want to show that the maximum degree in the complement of the graph is at least 2n over 3, where n is the number of vertices. So here's an idea we can use. Say in G, in this picture, G has three components. There's A vertices here, B vertices here, C vertices here. In G complement, since in the original graph G, and these are different components, so I don't have any edge going from here to here, that means in the complement, I would have every edge going from here to here. So in the original graph, since these are different components, I don't have any of these edges, any of these edges, or any of these edges. In the complement, I would have all of those. So the degree of a vertex, if I just choose a vertex in here, the degree is going to be at the very least, the degree in the complement. The degree in the complement is going to be at the very least all of these vertices plus all of these vertices. So it's going to be at least B plus C. Of course, I could do that wherever I want. I could choose a vertex in here, and then in the complement, the degree would be at least A plus C. Or here, I could put this, and the degree in the complement would be at least a plus b. We're interested in the maximum degree in the complement, so I should do whichever one of those will give me the largest degree. So what I'm going to do, going back to what I wrote, suppose we have suppose the three components, and I can make that more clear here, in G have A, B, and C vertices, where A less than or equal to B less than or equal to C. So I just arbitrarily said let A be the smaller one, B is the one in the middle, and C is the biggest one. So of course A plus B plus C is N, because that's the total number of vertices. And since I said A is the smaller of the three, A is less than or equal to a third of the vertices. So let V be a vertex in the component with A vertices. So just like I drew, it's here. And notice that I'm choosing V to be in this set, the smaller component. A is the smallest of the three. Well, there can be ties, but A is less than or equal to the other two. And I'm doing that because I want the degree in the complement to be as large as possible. So the degree in the complement, the degree of V is going to be at least B plus C, and I like that because those are the larger two sets. And I want the degree to be as large as possible. So yeah, now I just calculate how large the degree really is, and it turns out to be what I want. So in G complement, G would be adjacent to at least, I could say B plus C, or I could just say N minus A, because those are the same thing, right? So V is adjacent to at least N minus A vertices, and since A is at most N over 3, N minus A is at least 2N over 3. And so the degree of V in G complement is at least this much. So we found a vertex whose degree is at least this much. That means the maximum degree in the complement is at least that much. Okay, so yeah, maybe I'm done for now, so I'll upload this.